Hello everyone. In this video, we are going to talk about Generalized Hough Transform or GHT, which was developed in 1981 by Dana Beller. And the power of this method is you can detect arbitrary shapes, okay? As opposed to the Hough Transform, if you watched my computer vision image processing playlist, you see I have two videos on this. One, I talked about the theory of it and showed the code in MATLAB. The other one, I showed it in OpenCV. But the Hough transform is really meant to detect lines and circles. Now, some might say ellipses as well, but really it's just simple parametric shapes that have for lines two parameters. Remember, it was this rho and theta. And for circle, three parameters, x, y, and r you can give it a range also. But if your shape is arbitrary shape like this, an arbitrary edge map of the shape, and you want to detect that in the this template, basically you want to detect it in a bigger image, what can you do? And this method is the solution. So what does this method do? So here you define what we call a reference point, which most of the time is the centroid of that edge map. So let's say this is your edge map of the arbitrary shape, and this is your centroid or reference point. And you now basically parameterize the curve with respect to this center point or reference point, and you form what we call an R table. So what is that here? So at each point on the edge, you find the tangent to the edge or the gradient, the local gradient. The angle of it, you call it phi. Okay, then what? Then from that point to the center or to this reference point, you find the radial distance r and you find the angle with respect to the horizontal axis alpha. And so you form this table called the R table, where the points are basically parameterized based on their phi. So at phi of 0, there are some points that have some value of r and alpha, and then at phi of delta phi and 2 delta phi and so on, right? You can find all of these basically different r's and alphas. And the fact that you see more than one r and one alpha is because, for instance, let's say phi is 0. So is there only one point on the edge where the tangent line is flat or horizontal? No. I mean, like if you look here the gradient is flat, so phi is 0. If you come here, probably you have it. If you go there, maybe you have it. If you come here, maybe you have it, right? So per each phi, there could be several sets of r and alpha. That's why you might call them, for each phi I, you call them r, I, and k, and alpha I and k. Okay, so you form this table. Good. That's the first step. Construct the R table. Now, once the R table is generated for the template image, now you want to search the template within the target image. So let's say here, this is my target, the triangle this time, and I want to find it within this target image. Okay, so triangle, there is no method that is designed specifically for triangles or any arbitrary shape like this. So what do? I form my R table for this specific triangle. Good. Now what? Now the goal is to find in this template image the center or this reference point that are possible. So basically I say, hey, in this target image, where can I find centers XC and YC that match this R table that I have? Okay, with this R table, that everything is formed based on XC and YC, how many potential XC, YC candidates exist? And I go and I find there is one here, there is one here, and there is one here that can describe such match. You might say, what about here? Would you get that? No, because the R table that you get for the circle is definitely going to be different than the R table that you get for a triangle. since I form my R table based on the triangle when I find potential XC, YCs, and I'm going to explain how. When I find potential XCs and YCs, the XCs and YCs that are not for triangle, they will not get high votes. They will not be maximum in what we call this accumulator array. And so they will be suppressed, and only the ones that are high for triangles will be selected, and I can find them. Okay, now how do we do that? Let's talk about this. So the first thing you do, you quantize your parameter space XC and YC. What does that mean? It means you form a table. In this case, you only have two parameters to find XC and YC, correct? So XCs are on the, let's say, horizontal axis, YCs are on the vertical axis. So this is going to be your XC minimum all the way to XC maximum, and then YC minimum all the way to YC maximum. Okay, and what numbers could they be? Well, definitely they could be from 1 to the width of the image and 1 to the height of the image. That's all you can have. Your pixels should be within that range. But still, you see, it's a big space, right? So that's where, if this target image is a large image, the search is going to take some good time. So the smaller the target image and the template, it is going to be better. So I recommend, if your computer does not have a ton of memory and a ton of computational resources, lots of cores, make sure to resize these images to smaller sizes so you can reduce the size of this search space. Okay, so you quantized it, good. So they go pixel by pixel. Now what? Now in the target image edge map, by the way, this method works based on the edges. So you have to convert all of your everything into edges, right? Remember that we are working on the edges, so not just grayscale edges. Now, for each point X and Y in the target image edge map, for each that, using the phi, retrieve from the R table the R and alpha values under each phi. So you go, let's say, with phi of 0, correct? You go with phi of 0. And then you see, well, for phi of 0, I have these sets of R's and alphas, correct? Yes? And, of course, each one of them had some corresponding X and Y, correct? So in the target image now, not the template image, in the target image for each X and Y, using the phi, you're going to go. So what does that mean? It means, let's say I'm here at this position X and Y. At this X and Y, I go and look under phi of 0. Good? I find R1 and alpha 1, R2 and alpha 2. Let's just focus now for one set of them, R1 and alpha 1. I say, well, if I'm at location X and Y right now, where could the center be? If I'm at location X and Y, and for a moment assume that this X and Y is one of the points on the edge map. Now, it's not necessarily, as I just showed you, this point is not on edge map of a triangle. But if it was, where would the center be? Knowing that I know the radial distance R and alpha, if this point was on a triangle, where would the center be? Well, it's very easy to show that XC is equal to XI plus RI cosine alpha I, and YC is YI plus R sine alpha I, correct? It's a very simple trigonometry here. So I calculate based on that X and Y location and the R and the alpha I read from the table of that template. I find some XC and YC. Okay, and let's say that XC and YC comes here. So I say, well, based on where I am and the R and alpha I found from the table, this point here in the image should be maybe here, for instance. This could be a potential basically center, correct? Yep. Or actually, if you want to go with the triangle, depending on, well, I don't, phi of 0 is like this, so it should be above it. So in this case, your center would be somewhere probably here. Okay, so I found that. That is the center. If it was on a triangle, that would be the center for it. Then I go and look at the other phi's. So I find all the other phi's. Now for triangle, you only have 3 phi's really. It's easy. You only have phi of 0, phi of 60 degrees, and phi of 120. That's all the phi's you have. You only have 3 rows. So I go here and say, well, if this was on a phi of 60, then probably the center would be here. Now, if center is there, I would not even bring it into the table because it's outside the image. So that is out of the scope. I'm not going to even bring it. If it was on phi of 120, which was here, then the center would be probably somewhere to the right of me. So that would be the center. So there, for instance, I have like this point as my vote. Good. So this green point will suggest these 2 red crosses as potential centers. Based on all the phi's and all the r's and alphas in the table, it gives these votes. Then I move this green point, I bring it here, for instance, right? And this one is going to suggest basically, again, different centers. So you get one center here, maybe one center there, one center there, and you move this x and y all over your target image, and you get tons and tons of these potential xy's, correct? Stuff like that. And then once you get all these votes in, you're going to see that some places in the target image, you have some local maxima. In this case, the local maxima happens here in the image. It is going to happen here in the image. And it is going to up here. It is going to be up here. So once you have this, you are going to find 3 potential centers in the image, 3 potential maxima. There will be some other maxima, but they are not as big as these guys. So you have to do what we call a non-maximum suppression and find the largest ones, and then you're going to show them. And this is what you get. And this is that result of running this and getting that accumulator array. So this one here, which we call accumulator array, this one is right there for this image. As you can see, there are some local maximas. There are some other maximas, but they are not as big as these guys. You see, I have something here, here, right? But they are no big as these guys. So if I want to get the largest ones, these 3 are my largest ones, and as you can see, they exactly identified the correct centers. So look at these. You see, I exactly found these centers, and one beautiful thing about it is what? Look at this case. Here, the edge map is not complete. There is either noise or occlusion. Most of the time there is occlusion. One object goes behind other objects. And this method, like the original Hough transform, is powerful enough to detect it. So if we talk about the advantages of this, first of all, if the shapes are a little bit deformed or partially deformed, it can detect them. If there is under occlusion, they can detect them. Okay, so if there are additional structures and occluding, it detects them. If there is noise, it can detect them. If there are several occurrences, it can detect them. But as you can see, it needs a lot of computations. It needs to do lots of computations because for each pixel, it has to go find one phi, find one r and alpha, and then find all of these centers, cast a vote, and then keep going. So imagine if, for instance, your image has what? Your target image has, I don't know, 300 by 400 pixels. Okay? And if your R table, in this case, let's say I only have 3 phis for a triangle, and for each one, basically when I form the R table, well, how many points you can consider on this? Okay, but let's say, for instance, 50 points per edge. So you have 50 pairs here in each row. So it is going to be times 3 times 50. You need to do these many computations of the center and then find the local maxima. Okay, so it needs a lot of computations. Now, here, one thing you might mention is, well, what if we want to find the scale and the rotation? So here my triangle is not rotated, and these triangles in the target image, they are not rotated as well. Now, of course, they are scaled a little bit, but not rotated. So if this triangle was rotated like this, would I be able to detect it? Okay, can we make this method robust to rotation? Or if it was scaled very small or very large, can you do a great job as well? Or can you detect the scale level and the rotation level, right? The rotation angle. Can you do that? The answer is yes, you can, but you have to bring that scale or the rotation as an extra parameter. So right now, the accumulator array that you have is 2D. There is only X and Y to search and form. But if there is angle, now it's going to be XC, YC, and angle. And if there is a scale, it's going to be XC, YC, angle, and a scale. So it's going to go 3D or 4D accumulator array. So forming that and searching that, especially forming that, is going to take a lot more computations. So once you bring these extra things, it is going to be very, very basically hard to calculate, and it might not be super practical. Now, here I show you a couple of scenarios. So if I want to bring in angle and scale, angle theta, rotation, and scale S, then the way that I form my XC and YC in that accumulator array is a little bit changed. How? So here you have point xi and yi, but you don't simply just add and subtract to ri cosine alpha I and sine alpha I. What you do is first you form this point x prime and y prime, which is r cosine alpha and r sine alpha. That's the relative position between the center and this point xi and yi. You form this vector, then this vector has to be rotated and scaled, right? Because when you shrink the shape or extend it or expand it, or if you rotate it, it's this vector that will be rotated, this basically vector from one point of the edge to the center of it, right? It is going to be scaled or basically rotated. So what you take from that x prime and y prime is first you rotate it by angle theta about the z-axis. So you get to the new point. So you first rotate it by angle theta, and then you scale it down by factor s. Now you're going to add it to the to the point of test, and that will give you your xc and yc. And clearly in this case, your accumulator array is going to be 4D, and you cannot even visualize it. So what I'm showing here is just a 2D version of it, which is only showing XC and YC and not showing theta and S, but just showing theta and S as something on the title. So what you can see down here is just theta. So in this picture here, the only thing that was extra to the XC and YC was angle. And I applied it on this arrow. So this is my template, and I wanted to find it in this image. And you see it clearly found it and says, hey, this is where it is. And it says the rotation was 270. And you see there are several maximas and so on, but this one was the highest one. So it picked this one as the maximum. Okay. And then here I brought the scale as well. So this one is bigger than this one. Okay. Or in this case, actually, it's smaller than this one. And I say, can you still find it? And you see, still could find it and say, hey, the scale was 1.2 and the rotation was 270. And this is the best point. Okay, so yes, it can do it. But when I run this code, and I'm going to show you when I run this code, it takes a lot more than just rotation added. And it takes a lot more than no scale or no rotation. Okay. And I'm running it on a Core i7. So if you have more cores or GPUs or something, it's not going to be a problem for you. Otherwise, it is going to be quite daunting task for the computer. So here is the code, and I'm going to share the code under the video description. Let me show you the code. And before we pass on, I'm showing you that the material is taken from Wikipedia. The pictures here, not these pictures I generated from my own code. But these two, this table and this one, as well as these formulas, they are coming from, and the algorithm, they are coming from Wikipedia. So here, this is the test code that I have written for my template image and the target image. And you see that first I convert them to a grayscale, then I run the edge map on them because this method works based on the edge map. Then I pass these edge maps to the generalized Hough transform, and it gives me an accumulator, basically array and R table. And then here what I did is I also added a non-maximum suppression function if there is more than one occurrence. So this function is also added so it can find more than one occurrence, and there is this parameter that you can choose 0.5 times max, so anything above 0.5 times max is considered. Okay, and you can change this threshold if you need to suppress more or suppress less. And in the first figure, I show you the occurrences. In the second one, I show you the accumulator array. And you see right now, so this is my generalized Hough transfer function. And you can see that there are lots of calculations. There are three nested for loops, and there is one if. This is for the function. But there are three here, right, that you have to go. And you can see that you find XC and YC and you add it to the accumulator. So this is relatively fast because I made my images small, boom, right? So it's very fast. And again, you can see that I could find this triangle, all three occurrence of that, and this one with occlusion basically, or a part of it partially available. And you can see that. And here, there are so many points that are close to each other. That's why you see a ton of crosses as opposed to one, but they are mostly overlapping here, here, and here. Okay, so this is one, and again, this is the accumulator array. You see there are some maxima, but these 3 points are the best points. Okay, so it is working relatively good. But now if I go and run this other one, which is running on the arrow, and this one takes into consideration the scale and the rotation, right? You see you have a lot more loops here, right? As opposed to 2 for loops, or 3 actually. Let's go back here. There are 3 for loops and 1 if. Here you have 5 for loops and 1 if, and the 2 extra ones are for a scale and rotation. Okay, here I ran it, and after a few minutes I could get it as opposed to a few seconds. So here is the result, and you can see that it detected the scale and it detected the rotation of this with respect to that one, and it is doing its job. And this is the accumulator array. As you can see, that is your best spot there, the maximum vote. And I have another one. Let me open this one as well for you. This one is for rotation only. Okay, so this one is for rotation only, no scale, because sometimes you don't care about the scale, you just want the rotation. So this one takes into account the rotation, so it has 4 for loops and 1 if. And so this is a little bit better, right? This is not as daunting as that one is. And so if you run this one, it should run a little bit faster. Okay, so this one only detects the rotation. Here you have a 3D accumulator array as opposed to 4D. Okay, so here is the code. You see the highest point is here, but it found a potential one there, but it's not as high as this one. So here I ran just the max command, not the non-maximum suppression one on this one that has rotation and rotation scale. I only use the max. Okay, I did not use the non-maximum suppression. If you want, you can modify the code in these two to use the non-maximum suppression code, just like I did for here. right? This is how I found the non-maximum suppression by this threshold that you can adjust, and then I show the peaks. But clearly you can see that it found it. It found the angle is 270, no scale search, and this is the accumulator array. And it works well whether there is occlusion or not occlusion. This is a really powerful method. So hopefully you enjoyed this video. As I said, all of these several files, there are 7 files here, 4 functions and 3 test scripts. Along with the images, I am going to put them in a zip folder and give you a download link on the video description. Hopefully this is useful for you if you have any research or any work that needs detecting arbitrary shapes. And these files, as you see, I ran them and they are completely functional and working. Thank you so much. I'll see you in the next video.